Okay, everyone. Well, I am home with my son who is sick, so we are going to go through practice via this video instead. Okay, so we want to find the equation of the line tangent to f of x equals x squared plus 3 at the point -2, 7. Okay, that is going to, we are going to have to make use of derivatives, which is what you guys looked at last night for homework. Okay, and essentially a derivative just means slope. So if I want to know the slope of that line, I need to take the derivative. Okay, normally if we had just a regular line, a straight line, you could use rise over run. Okay, but in this case we have a parabola with x squared plus 3, so the slope isn't constant. Okay, so we take the derivative and that gives us the formula for the slope at any point. Okay, so we have the equation, let's see, limit as x approaches -2, okay, of, let's see, x squared plus 3 minus whatever f of 2 is, so that would be 2 squared plus 3 all over x plus 2, okay, which is x minus -2. When we do the algebra for that, okay, we get x squared plus 3 minus 7 all over x plus 2. And then when we simplify, we get x squared minus 4 over quantity x plus 2. Okay, we can factor that. Okay, so we have an x plus 2 times x minus 2 all over x plus 2. Okay, and upon direct substitution, we would get -4. Okay, so what that means is that the derivative at the point -2 is -4. Okay, and we would write that f prime of -2 equals -4. What that means is that the slope of our tangent line when x is -2 is -4. Okay, so if we want to find what our tangent line is, we can use -4 as our slope. Okay, and we have the point -2, 7. So we're just going to plug that into point slope form. So we have y minus 7 equals -4 times quantity x plus 2. Okay, and this is a perfectly acceptable solution, and you can leave it in point slope form. If you would prefer, you can write it in point and slope intercept form. Okay, so that would be, say, y equals -4x minus 1. Okay, and that is the tangent line at 2 f of x equals x squared plus 3 at the point -2, 7. Okay, now if you were to graph these two things, so if you were to graph f of x equals x squared plus 3 and this tangent line, you would see that it is in fact tangent. Okay, so if I had, I'm just going to do a rough sketch off to the side here, okay, but you could do that on your graphing calculator as well. Okay, so when I graph this, okay, if I have x squared plus 3, well that's a parabola, right here. Okay, looks something like that. Okay, then if I want to graph my tangent line, so y equals -4 x minus 1, okay, we know that it looks something like this. Okay, and you can see that our tangent line really is the tangent line at that curve. Okay, so you can plug those both into your graphing calculator and check that out for yourself. Okay. Next, we want to find the derivative of g of t equals 3t minus 2. Well, just thinking about that for a minute, I said that derivative is just slope. Well, in this case, we should know what slope is just looking at that, okay? So just using what we know about the word derivative, if I look at that, I should say, well, my slope is 3, so my derivative should be 3. Okay, so let's give that a try. Okay, in this case, we can't use our alternate form of derivative because it's not asking for a derivative at a point. Okay, so we have to use the limit as, we're going to say delta t approaches 0 of g of t plus delta t, so that's t plus delta t minus 2, okay, minus just g of t, that's 3t minus 2, all over delta t. Okay, so when we work this out, okay, that gives us 3t plus 3 delta t minus 2 minus 3t plus 2 all over delta t. Well, things should cancel. Okay, we have a negative 2 and a positive 2, a negative 3t and a positive 3t, okay, and then 3 delta t over t. Well, those delta t's cancel. Okay, that leaves us with the limit as delta t approaches 0 of 3, okay, which is constant, so our answer is 0. Okay, if I were to write that using the proper notation, I would say g of t, or g prime of t, is equal to 3. Okay, and what that means is that the derivative of that function is 3, always. Okay, and that makes sense because we said derivative is slope, and looking at that line, the slope was 3. Okay, so now we are going to use that result to find the equation of the line tangent to g at t equals negative 4. Okay, so let's see here. We know that g prime of t is 3. I know that t is negative 4, so that if I plug that in, I'd get the point negative 4, 12 minus 2, negative 14. Okay, and I got that just by plugging in that negative 4 into my equation. Okay, and then if I know that g prime of t is 3, really I need to find out what g prime of negative 4 is. Well, if I plug in negative 4 into that function, I still get 3. Okay, so the slope of our line is going to be 3, and we are going to use the point negative 4, negative 14. Okay, so when we do that, we get y plus 14 equals 3 times x plus 4. Okay, so this is the equation of the line tangent to g at t equals negative 4. If you want to go further, you could find it in slope-intercept form. Okay, and if we did that, we would end up with y equals 3x minus 2, which should make sense. Okay, that's actually the very same thing that we started with here. Right, that's the same as this. Let's write another color. It's the same as this. Okay, and that should make sense because if I, just thinking about it graphically, okay, if I have 3t minus 2, okay, it should look something like this. Okay, and I want to know the graph of the equation tangent negative 4, that's this. Well, it's going to be the same thing, right? It's going to be the exact same thing if it's going to be tangent to the original curve. Okay, so it makes sense that we would get the same thing out. Okay, next we need to find the derivative of f of x equals 2 over x. Okay, so again we need to use our definition of derivative. So that's the limit as delta x approaches 0 of 2 over x plus delta x minus 2 over x all over delta x. Okay. All right, well that's a little bit messy, right, because we have complex fractions there. Okay, so we need to combine those. Okay, so we have limit as delta x approaches 0. Okay, if I want to find common denominator, it's just going to be x times x plus delta x, so that'll give me 2x over x times x plus delta x minus 2 times x plus delta x over x plus delta x. Okay, and that is going to be all over delta x, or I can think of that as times 1 over delta x. Okay, so if I wanted to divide by delta x, it's the same thing as changing it to multiplication, flipping it, so multiplying by 1 over delta x. And I realize I lost an x there in my denominator. Okay, so let's combine that. Okay, that gives us a 2x minus 2x minus 2 delta x all over x times quantity x plus delta x times a delta x. Okay, well, combining like terms, I can cancel out these guys. Okay, 2x minus 2x is 0. Okay, and then I can reduce by delta x, because that is a factor in both my numerator and denominator. Okay, that leaves us with the limit as delta x approaches 0 of negative 2 over x times x plus delta x. Okay. At this point, we can just do direct substitution. Okay, if we do that, we end up with a negative 2 over x times x plus 0. Okay, well, that is a negative 2 over x squared. Okay, and what that means for us now is that the derivative of our function, okay, I can write that as f prime of x is equal to negative 2 over x squared. Okay, and that means that if I want to find the slope of the tangent line at any point, I can use that function. Okay, and we will actually be doing that in part 5. Okay, so it says use your result from number 4 to find the equation of the line tangent to f at x equals 1. Okay, so in order to find the equation of a line, I need the slope and I need a point. Okay, well, to find the slope, what we're going to do is we are going to use our derivative. Okay, so we had f prime of x. Well, I want to know the slope at 1. So we're going to use f prime of 1 is equal to negative 2 over 1 squared, which is negative 2. Okay, so the slope of our tangent line when x is 1 is negative 2. Okay, and then we are going to find our point. Okay, well, if I want to know, I know f of 1 will be 2 over 1, okay, which is 2. Okay, so what that tells us there, doing that work, let's get rid of that there. Okay, so what that tells us then is that the slope of our tangent line at 1 is negative 2, and the point 1, 2 exists on our graph. Okay, so we're just going to plug that in to point slope form. So we have y minus 2 equals negative 2 times quantity x minus 1. Okay, and that's a perfectly acceptable form to leave it in. If you wanted, you could change that to slope-intercept form, and then you would have y equals negative 2x, plus 2, which is y equals negative 2x plus 4. Okay, and if you were to graph the original function, which is f of x equals 2 over x, and then you were to graph that tangent line, y equals negative 2x plus 4, you should see that it really is a tangent line at the point when x is 1. Okay. Okay, now what you're going to do is I have some practice problems for you that should be handed out to you. There are 6 of them, 3 on the front, 3 on the back. So give those a try. The answer key I left there, so when you guys finish, you should be able to check it over. Okay, once everyone has done that, I'm guessing it should take maybe 15 minutes or so, then you can push play again to this, and we will see the last little bit. So push pause, do the problems, push play. Okay, now we're going to talk about differentiability and continuity. We say that a function is differentiable at a point if its derivative exists there. Okay, and there are 3 distinct times when a derivative fails to exist. Okay, first off, it fails to exist when a function is not continuous at x equals c. Okay, the derivative also fails to exist when the derivative from the left and the right do not agree at x equals c. Okay, an example of that would be like if you're thinking of something, let's say like an absolute value equation. Okay, if I'm looking at the slope from the left and the slope from the right, they're not the same thing. Okay, so the derivative does not exist. And then the third is when the graph of a function has a vertical tangent line when at some value x equals c. Okay. In all of these cases, a derivative fails to exist because a tangent line fails to exist or because the tangent line has an undefined slope. So remember, a derivative is just the slope of the tangent line. Well, we can't find a derivative if a tangent line doesn't exist or if the slope is undefined in the case of a vertical tangent line. Okay. So we are going to just work through a few different scenarios with differentiability here. So first off, if a function is differentiable at x equals c, then it has to be continuous at c as well. If it's not continuous, well then the tangent line can't exist, so we can't have the slope of the tangent line. Okay. So if a function is not continuous at x equals c, it cannot be differentiable at c. Okay. So as an example, if a function is not continuous at x equals c, it's automatically not differentiable. Okay, so we can look at the greatest integer function. We actually pretty recently talked about this, so hopefully it's fresh in your mind. But just in case, okay, this function, essentially if I put an integer into this function, it gives out whatever the greatest integer was right before the integer that I put in. Okay, or up into including, I should say. So if I put in 0, it spits out 0. If I put in, let's say, 0.2, it spits out 0. If I put in 0.7, it spits out 0. However, then once I put in 1, I'll get 1 out. If I put in 1.3, I get 1 out. Okay, if I put in, let's say, 2.3, I'm going to get 2 out. So it's whatever the greatest integer was that's right before whatever value I'm putting in. Okay, if I were to graph that, it's a step function. Okay, it looks something like this. Okay, and this is a function that you guys should be familiar with. It does come up from time to time. Okay, so let's see, looks like this. Okay, there we go. All right, so if I wanted to say, let's look at, I don't know, say let x equal, we'll do 1. Okay, well, if I look at the limit as x approaches 1 from the left, I end up with 0 as my limit, right? As I'm coming in here from the right, okay, my limit is 0. Well, as I'm approaching x from the left, right, my limit in that case is 1. Okay, so that means that the limit as x approaches 1, okay, does not exist. Well, if the limit doesn't exist, it is not continuous, and therefore it's not differentiable. Okay, and thinking about it, I can't, it's impossible for me to draw a tangent line right here, right? We just can't. So if we don't have a tangent, there's no way we can have a slope of a tangent. Okay, so that function is not differentiable there. Okay, next scenario is that if a function is continuous at x equals c, that doesn't necessarily mean that it's differentiable at c. Okay, so as an example, if the graph of a function is a sharp turn, the derivative from the left and the derivative from the right will not agree, but the function will still be continuous, just not differentiable. Okay, so to start off with, it's kind of difficult to work with absolute value equations, so I'm going to break that up into a piecewise function. Okay, so instead of saying f of x equals absolute value of x minus 3, I'm going to think about that as f of x equals, well, when x is greater than or equal to 3, it's just x minus 3. Right? If I plug in 3, I'd get 0. If I plug in 4, I'd get 1. Okay. it would be a little different if we have x is less than 3. So when x is less than 3, let's say I put in 2. I'd have 2 minus 3, that's negative 1. I'd have to take the absolute value of that. So essentially I'd be multiplying it by negative 1. Okay, so we have negative quantity x minus 3. Okay, when x is less than 3. Okay, so that is our function there. Okay, it's just written as a piecewise function. So now we're going to use the definition of derivative to look at this function as we approach 3 from the left and from the right. Okay. So limit as delta x, in this case we're approaching 3 because that's kind of our point in question there. From the left, okay, we are going to use negative x plus delta x minus 3, okay, minus negative x minus 3, okay, all over delta x. Okay, when we do that arithmetic out, okay, that gives us a negative x minus delta x plus 3. Let's see, and then we have a plus x minus 3. Okay, all over delta x. And there's a couple negative signs you have to be careful with there. Okay, so now let's simplify where we can. We have a negative 3 and a positive 3. We have a negative x and a positive x. And then I have negative delta x over delta x. Okay, that simplifies to negative 1. Okay, so that gives us the limit as delta x approaches 3 from the left of negative 1 is just negative 1. So the derivative as we're coming in from the left is negative 1. Alright, well now let's check it out from the right. Okay, from the right, we're going to use the bottom portion of that piecewise function. So we're going to say limit as delta x approaches 3 from the right, okay, of, let's see, so we have an x plus delta x minus 3 minus x minus 3 all over delta x. And this is a little bit easier just because we don't have all those negative signs there. So limit as delta x approaches 3 from the right of x plus delta x minus 3 minus x plus 3 over delta x. Okay, so again, we can simplify where we can. So we have a negative 3, positive 3, x, negative x, delta x over delta x is 1. Okay, so that leaves us with the limit as delta x approaches 3 from the right of 1, which is 1. Okay, so from the left, the derivative is negative 1. From the right, the derivative is positive 1. Okay, so this function is not differentiable, even though it's continuous, and we could show that using the definition of continuity. You're welcome to do that on your own if you'd like. Okay, but this is enough just to show that the derivative is not differentiable, which is what we were going for. Okay, and then lastly, okay, a function is not differentiable at x equals c, or just because a function is not differentiable at x equals c doesn't necessarily mean that it's continuous at c. Okay, so we could have shown that in our last example, but here's another example. If the graph of a function has a vertical tangent line at x equals c, the function is not differentiable at that point. Okay, the function will be continuous, the left and right limits will agree, but the function will not be differentiable. Okay, so we can look at f of x equals the cube root of x. Okay, and those green marks are just, you can ignore them. Okay, I'm going to just consider the point x equals 0. Okay, and that's really because I have some insider information here. Okay, so if I want to take the derivative at that point, so the limit as delta x approaches 0, okay, using f of x minus f of 0 over x minus 0, I get root 3 of x minus root 3 of 0 over x minus 0. Okay, that gives us root 3 of x over x. Okay, and then using what do we know about rational exponents, okay, we can rewrite this as limit as delta x approaches 0 of x to the 1/3 over x, okay, and putting everything into the denominator, we get 1 over x to the 2/3. Okay, now if I were to just do direct substitution, I would see that I get 1 over 0, okay, and so that limit does not exist. Okay, it'll approach positive infinity, but we don't care for right now, it doesn't exist. What that means is that this function is not differentiable at x equals 0. Okay, we can show that that the limit doesn't exist. If the limit doesn't exist, it's not differentiable because a derivative is just a limit. Okay. However, it is continuous, okay, and I'm going to show you that. Okay, so it is continuous when x is 0 because first off, f of 0 exists. Right? It is 0. Okay, secondly, we can show that the limit exists. Okay, so the limit as x approaches 0, okay, we just use direct substitution and we get 0 out. Okay, before using derivative, we had a special definition of, well, it's the definition of derivative, so we use limits, but it's not quite the same thing as just taking the limit of the function. Okay, and then for 3, I can show that f of 0 is equal to the limit as x approaches 0 of the cube root of x. Okay, so that shows that this function is continuous at x equals 0. It's just not differentiable at x equals 0. And the reason for that, graphically, okay, is that cube root of x, okay, looks like this. Okay, so the tangent when x is 0 is actually a vertical line. Okay, and we know that derivative is just slope of our tangent line. Well, a vertical line, the slope isn't defined, so therefore the derivative is not defined there, and so it is not differentiable at that point. All right, so you guys do not have any other videos or notes to do for Friday, but you do have a problem set that's due Friday. So look it over. There's only a few questions, some of them just dealing with continuity, some dealing with derivatives. If you have questions, come see me before then. And I hope that you guys have a good day. Alrighty, that's it.